Hello students, this is AMOL INGOLE. In this video, I'm going to explain convolution encoder using generator matrix. In earlier videos, you discussed that convolution code can be described by the generator sequences. Generator sequences actually specify convolution code completely by the associated generator matrix. That means we can use the generator sequence to construct a generator matrix which actually specify the convolution. The encoded output of the convolutional code is obtained by matrix multiplication of the input bit stream and the generator matrix. That is V is equal to UG. So it is similar to the LBC where we obtain the linear block code by multiplying the message block with the generator matrix. Let us see how this matrix, generator matrix, can be obtained. The generator matrix for convolution encoder can be obtained by interlacing the generator sequences G1, G2, and so on in the manner shown below. For this, we are going to consider the block size of the convolution encoder as nkm, where n is considered as 2, k as 1, and there will be m number of memory units or shift registers. The generator sequences can be written in this way, where this is generator sequence G1 and it will have m plus 1 number of beats as a length of the generator sequence. This is G2, which will again have the same number of bits like in G1. The first row of the generator matrix is obtained by interlacing the generator sequence G1 and G2, and it is shown like this. You can see the first row of the generator matrix, and it is obtained by interlacing G1 and G2 generator sequences. You can see here, this is G1 0. This is the first beat of the generator G1. G2 0. This is the first beat of the generator G2. Then you can go on interlacing the remaining beats in the same way. Like this is the third bit of the generator matrix, which is nothing but G11, second bit of G1 is interlaced with second bit of G2, which is G21, G21, and so on. This is how you will get the first row of the generator matrix. The number of column of the generator matrix depends on length of the input given, length of the input bit stream given. So as that input bit stream is not known, we will try to construct a generalized generator matrix. The second row or the next row of the generator matrix is obtained by shifting the previous row by n spaces. The example that we are considering here is having n is equal to 2. So the next row, in this case the second row of the generator matrix, will be obtained by shifting the first row by 2 spaces like this. Why 2 spaces? Because n is equal to 2 here. There are 2 generator sequences given, G1 and G2. If we would have given 3 generator sequences, in that case we would have shifted the previous next row with 3 spaces. So you just need to shift it right by 2 spaces. N is equal to 2 in this case. And the remaining rows can be obtained the similar way. This is the third row, which can be obtained by shifting the second row by 2 spaces. So second row is shifted by 2 spaces more, and you will have 4 zeros here. 2 already are there in the second row and 2 more after shifting. So total 4 zeros and the same generator sequence interlacing. You need to go on repeating these steps, and the number of rows again depends on the input bit stream length. The generator matrix is a semi-infinite matrix as the input is continuous stream. So that's why in the example we did not show the number of rows and columns because it depends on the input bit stream. So the size of the generator matrix would be semi-infinite. For a finite length input, let us say the input bit stream has x bit in it, G will have x rows. The number of input bits is equal to number of rows of generator matrix, and the number of columns will be equal to n into m plus x, where n is number of output bits. In this case, in the previous case, we considered 2 bits, n is equal to 2. M is nothing but number of memory units, and x is nothing but length of your input bit stream. So those many number of columns you will have in generator matrix. Size of the generator matrix will be x by n into m plus x. That's how you can show here the size of the generator matrix. We'll see one example of convolution encoder using generator matrix. The statement of the numerical is impulse responses G1 and G2 for the convolution encoder are given as G1 equal to 1011. This is the generator sequence G1, and the generator sequence G2 is 1111. You're supposed to construct a generator matrix G, draw the convolution encoder, and encode the input string U. So here the input bit stream given as 10111. Let us solve this. If you read the statement, you will find that there are 2 generator sequences given, impulse responses given. So that means there will be 2 output. Therefore, n is equal to 2. K will be equal to 1. At any instant of time, only 1 bit will enter the encoder. And the input bit stream has got 5 bits in it. U is equal to 10111. It has got 5 bits in it. The length of the generator sequence is 1 more than the depth of the register. That means the generator sequence has got 4 bits in it. So the number of memory units required will be 3. The constraint length can be obtained using this equation, and C is equal to n into m plus 1, and that will be equal to 8. The constraint length actually tells you the number of output bits every input bit is influencing. The given encoder is a 213 encoder. It is NKM. This is the given input stream, and the size of, as we have got a finite length input bit stream, so we can write the size of the generator matrix, and it is given by X, which is length of the input bit stream. In this case, it is 5 by n into m plus length of the input stream. So it will be 16. That is, n is 2, m is 3, and length of the input bit stream is 5. So 5 plus 3 is 8. 8 into 2 is 16. So size of your generator matrix would be 5 rows and 16 columns. Let us see how we can construct the generator matrix. There are two impulse responses given, and those are G1 and G2. You can actually write them like this: G1 0, G1 1, G1 2, G1 3, and the G2 generator sequence can be written as G2 0, G2 1, G2 2, and G2 3. Let us construct the generator matrix for the convolution encoder. This is what we have already discussed, how the first row of the convolution encoder is obtained by interlacing the generator sequences. So if you try to construct the first row of the generator matrix by interlacing the generator sequence G1 and G2 like this, first bit of G1 is 1, first bit of G2 is 1. So the first two bits in the first row of the generator matrix will be 1 1. You can see this here, 1 1, and this 1 1 comes from 1, that is first bit of the G1, and 1, which is first bit of G2, 1 1. Next two bit will come from second bit of G1, that is 0, and second bit of G2, that is 1. So 0 and this 1 will be the next two bit. Next two bit will be obtained by using the third bit of G1, that is 1, and here third bit of G2 will be 1. So 1 1 will be the next two bits. In the same way, you can write the last two bits of the non-zero bit, you can say, which is 1 and 1. And the remaining columns of the first row will be filled with all zeros, because we know this actual size of the generator matrix, and it has to be 5 by 16. We could only get 8 columns by interlacing G1 and G2. So the remaining columns will be filled with zeros, because we'll need here 16 columns. We could only get 8 columns by interlacing G1 and G2. So the remaining columns will be filled with zeros. That's how you get first row of the generator matrix. The next row, that is in this case second row of the generator matrix, will be obtained by shifting the first row by 2 spaces. Why 2 spaces? Because n is equal to 2 here. Why 2? Because there are 2 generator sequences. So n will be equal to 2. There will be 2 output. So by 2 spaces, if I shift the first row, you get the second row here. Third row can be obtained by shifting the second row by 2 spaces again. Fourth row can be obtained by shifting the third row by 2 spaces, and that's how you can get all 5 rows of the generator matrix and all 16 columns of the generator matrix. Once you have the generator matrix ready, you can now find the output of the convolution encoder by multiplying the input bit stream U with the generator matrix, just like we did in LBC. The output of your convolution encoder will be multiplying your input bit string U with the generator matrix, and this is what you will get it. The multiplication will be performed in the modulo 2 arithmetic fashion, rows into column. Thank you.